here, actually let's put a heading. So this would be 7.6 Salient Pole PM machines. So salient means sticking out, basically. Can you all see that? Okay, the back. Is that big enough? Yeah. Okay. So so if we look at the rotor 1, then we can see that the rotor has 2 norths and 2 souths. So if we were to plot the flux here, then we're going to have you know, a north-south type of field as a function of angular position. But then if we were to plot the inductance for a particular phase, for example, then with regard to the saliency, you can see there it's if we neglect the relative permeability of the magnets. So this is a slight approximation, but because the rotor is perfectly smooth, there's no ferromagnetic poles sticking out, then the inductance is constant. So again, if we're neglecting the relative permeability of the magnets, then the magnet is like air. So that if you have a stator on here, it would not matter what position we're in. The inductance with regard to the d-axis, which is defined on the magnet here, is going to be the same as the q-axis, which is defined as off-axis from the magnet. So then LD and LQ would be the same because again, there's no saliency. So then if you now look at this rotor here, and I think we talked about this in electric machines analysis class, then clearly there's no magnets on here, so there's no flux on the due to the rotor, which is not interesting. But then there's clearly, if you look at the d-axis relative to the q-axis, there's a clear difference in the saliency. So if you recall that the inductance is equal to n squared over reluctance if we're using magnetic equivalent circuits, right? Then you can see that the reluctance along the q-axis, because this is all air, is going to be way larger than reluctance along the d-axis. So therefore, so we have that RQ is going to be much greater than RD. Let me know if that's too small. You can read it? Do I need to make that bigger? That's fine? Okay. Okay. So then since the inductance is the inverse of the reluctance, then if the reluctance and the q-axis is really big, then the inductance in the q-axis would be quite small. So LQ will be much less than LD. Okay. So then there's if we plotted the inductance around as a function of angular position, you know, this inductance would be calculated where there's a stator as well. Just keep that in mind, of course. Then it would. This is an approximation. It's not going to be a beautiful sine wave, but it's going to have some maximum, some minimum corresponding to the maximum of LD and the minimum of LQ. So there's saliency. Okay, and so then moving on down, if we now consider this rotor here, this rotor has now got magnets put on the tips of the poles of the rotor. Now note, and here the d-axis is aligned with the magnet. That's the general standard for d-axis definitions. So if you look at the next one down, you can see now on this one the d-axis is defined here coming out from the magnet, and the q-axis is coming out of the ferromagnetic pole. So that may look confusing if you compare this bottom one with the second one, but when the magnets are included into the rotor, the standard way of defining things is that the d-axis is in the direction of the magnetization flux from the rotor. So if we can consider either of these really. They have the similar type of thing. So the flux as a function of angular position is going to be sinusoidally varying, ideally, and then on top of that we're going to also have some change in inductance, rotor inductance, because of the saliency in the rotor. So in this case, so on this one here, the d-axis has the smaller reluctance. So we would have the RD is going to be smaller than the Q, and so then that means that the LD is going to be much greater than LQ. It's going to be opposite. So this one has both rotor flux and saliency present. But this is a kind of a bit odd that you'd that the magnets would be put along the corresponding exactly with the salient pole. In this one here, you can see that they are aligned differently. So in this one, the reluctance along the d-axis is going to be greater than the reluctance along the q-axis. So the RD is much greater than the Q, so then the LD would be much less than the LQ. So right, that makes sense. Yeah. Okay. So then what we could define is a saliency ratio. Saliency ratio, and for a PM motor, for example, so that's going to be you could define that as LQ over LD, since usually the rotor would have a larger Q inductance than a LD inductance. So SR will be it should be greater than 1 if you add some saliency. The benefit, the negative of putting the magnet on top of the salient rotor is that, remember that the relative permeability of the magnet is close to 1, so you're introducing a really big air gap here. It makes much more sense to have the magnetic ferromagnetic material close to the rotor air gap, because then you have a lower you have a nice flux path to go around there. Okay. Any questions on that? Yeah.
So in the third one from the bottom, the flux and the inductance are going to be in phase with each other, correct?
Yeah.
And in the other one, they'll be 180 degrees out of phase.
They'll be yeah, they'll be out of phase. Mm-hmm.
Or 45.
Yeah. Well, it's yeah, they'll be out of phase, which is what you want.
Right. That's
yeah. Okay. That's why this machine is it's not a good one. So if we look at if we go to the next we go to the next handout. This one. This is just from JMAG, just showing something a little bit more realistic. This is like an interior permanent magnet rotor. So these rectangular pieces here would be the magnets, and then and this would be one set of laminations, stack of laminations with cavities in them, and then these other pieces on the ends, those are non-magnetic spaces. So the reason for that is because if you had magnetic material here, then the flux would take a shortcut through the rotor, and it wouldn't, we wouldn't get much flux going into the stator. So these are barriers. And then and these are magnets. So this type of topology is used in like the Toyota Prius, for example. It's got an interior permanent magnet rotor. So it has both the magnet flux, but it also has saliency, because if you look at if this is again, you define the direction of the d-axis with regard to the magnet, so flux. So then this would be the d-axis, and then the q-axis is going to be coming out here. So from an electrical point of view, the q-axis and the d-axis would have a 90-degree phase shift. And so in this one, the LD does not equal the LQ, right? You're going to have the LD being less than LQ, because RD is going to be greater than Q, reluctance. I have a hard time thinking in terms of inductance, but when I think in terms of reluctance, it makes more sense. So that's why I then do the inverse. Because when you look at the paths, you can see here the q-axis should have a low reluctance, because the flux could go through these gaps here and get past. But there's going to be, that's going to depend on the saturation in that magnetic material. Now if we then compare it to a surface-mounted one, you can see that the reluctance with regard to the rotor is pretty much the same. There is always going to be some difference. I mean, this is what I'm talking about here, is that they're not cut and dry, but you can see that the LD should be very close to the LQ in the surface-mounted rotor. Now, in this discussion, and in most discussions and in lots of papers, especially academic ones, they assume that the flux from the d-axis doesn't interact with the q-axis, and the current created from the d-axis that interacts with the d-axis doesn't interact with the q-axis, and so you can separate them. But in reality, all of the fluxes in the machine, like the d-axis flux is, I'm jumping ahead here actually. But the d-axis flux is a function of the ID and the IQ, and the q-axis flux is a function of the IQ and the ID. They're all interrelated somewhat, but so you have to really do a map of the fluxes with regard to both ID current and IQ current. So, but I'm jumping ahead here. But but what I'm going to say is that the discussion I'm going to talk about here assumes that the flux that the stator current will create that will interact with the d-axis only flows in the d-axis and doesn't affect the q-axis. So looking at this is just kind of cool looking plot here at the bottom. This is the saliency ratio LQ over LD, and so you can see that the surface mounted has pretty much 1, and as you go further and further across you get more and more saliency. So this one, this one, you know, a 2-layer interior permanent magnet machine. So that would mean that, you know, rather than having the 1 layer here of magnets, and the magnets don't need to be, they're often in a V shape like this. The magnets in the rotor, like this, but here it's just 1. But so you could imagine that these are these could have, you could have 2 layers where you have magnets embedded in them. You could even go to 3 layers with magnets embedded in it. But if you don't have any magnets embedded in it, you can still create you know, significant torque, especially when you have high saliency. The trouble with something like this is a axially laminated rotor. You could Google that and see some pictures. That would be that's just not practical from a production point of view, because these would need to be, these are laminations. You'd have to so you could think about this being these being laminations and having to form them into bends. So you're literally bending the steel into shapes like this and stacking it. It's not. It's cheap in terms of material cost, but manufacturing is a complete nightmare. Any questions on that? Okay. So, but it's not unreasonable to have salience ratios of 2 or around 2 and 3. So let's just look at a brushed DC motor briefly. So brushed DC motor equivalent circuit. So we've seen this before. So we'd have a so for a brushed DC motor, there's the rotor has a field current on it, and so that field current from the rotor then induces a voltage on the stator, and so this EA here is a function of the flux created from the rotor, and that flux is a function of the current that you apply if times the rotational frequency that the rotor is going at. So this is the psi f is the flux linkage due to rotor field current. Okay, and then and so we'd have VA is equal to IA RA plus LA DIA DT plus EA, like that. I'll call that equation 1. So now, if we think about the surface permanent magnet motor, then we don't have a field current on the rotor. We just have a fixed flux being created. We can't control the amount of magnet material directly on the rotor. So then, so surface permanent magnet motor. So in that case, in this one, then the LD, if it's just magnets on the surface of the rotor, the LD and LQ are very close, and we can say they're the same. So that, and then in steady state, then we would have something like this. Where ES is now equal to the frequency and the flux linkage, where the flux linkage psi m is due to the magnets on the rotor, flux linkage due to magnetic rotor. And I'll call this equation 2. So then the equivalent circuit for this is just IS RS plus J omega E LS IS plus ES. So now in this discussion, I'm going to neglect the resistances. It doesn't change the. It just, if I include the resistances, it just complicates everything, and you'll see that it's complicated. You'll realize that it's complicated enough. So you can add the resistances in. It's just going to add an additional vector into everything that we do from here on, but it doesn't really change the conclusions. It just would slightly modify them. So let's if we neglect the resistance, we can then say that we have Vs is equal to J omega E Ls Is plus Es, and I'll call that equation 4. So now, so we've got this nice little equivalent circuit, and then we could visualize what's going on with the a vector diagram. So again, this is for when LD is equal to LS. So if we consider the case where the current lags the voltage, IS lags VS, then we would have something like this. So this is the ES. This is from the caused by the rotation of the rotor, and then we have IS, and so IS is at an angle between the ES of gamma, and then we have ES and IS times omega E LS, and then that has to equal, so there should be a 90-degree angle there, and that has to equal the VS, which is here, VS. And so the angle between VS and IS is the power factor angle. Okay, so that's so we can draw the phasor diagram, and we can draw the equivalent circuit. So now if we look at the salient pole permanent magnet motor, and then there isn't a good equivalent circuit. I think it's often best to think about it in terms of the vector diagram, and then use that to look at the components. So we can look at the salient pole machine in terms of the d-axis and the q-axis coordinates, like I drew on the rotor. Splitting them up is makes the most sense. So but this d-axis and q-axis, the way I'm drawing it here, is a standard method where you can actually reduce all three-phase machines, rotating machines, into a d-axis, q-axis coordinate system. But I'm not going to go into all of the math on that here. But we will use the concept of the d-axis and q-axis when we think about it in terms of the rotor magnetization directions, because I think it really helps. So, and then it actually really gives you a physical feeling for what's going on, because you can look at D and look at Q and compare it with the machine. It's harder to do that, for example, in an induction machine, because in an induction machine you can also decompose it into D and Q, but there isn't some saliency. So here, so in this discussion, we're assuming that the resistance is 0. That again is to make things look simpler, and steady state. And so in this case, the LD will not equal the LQ, and so we need to decompose the current and voltage into DQ components. So the current component that is in the direction of them, that will create, so the ID current would mean that it is a current that is creating a flux that is in the same direction as the magnet flux, for example. Okay. Any questions on that? Okay, so it's tradition to, when doing the vector diagram, and it makes physical sense as well, as hopefully you'll see, tradition to align the q-axis along the ES axis, so along the direction that the induced voltage from the rotor flux is directed. And so if we assume that the ID current is positive first, so I'll show this. You'll see. I'll draw it for a negative as well, and then it'll make some sense. So let me just draw this. So we're going to have some ES that's due to the rotor. So ES is equal to psi m over omega e, where in this case psi m is equal to the d-axis magnetic flux. So we apply, based on tradition, align the ES with the q-axis and the DS along here. The US defines the d-axis as down relative to the q-axis. In Europe they have the d-axis up. So let's say that let me just draw this. There's a lot of bits and pieces going on here. So we'll have a current that would be associated with the d-axis, and then we'd have some current associated with the q-axis, and then both of them will result in a net current IS. Okay, and so we're just decomposing the currents. We could have done that here if we'd wanted to. If you see here, we could have defined this as the d-axis, and then this would have this would be the q-axis, and then here would be the d-axis, and then you could decompose the IS into d and q as well. But you don't have to do that with the surface permanent magnet motor, but you need to do it when it's this saliency. So because LD and LQ are separate, we need to put those two components together, and so they're going to have the ID times J omega LD. So that will rotate this vector by 90 degrees, and so we'll have a component along here, which is J ID XD, and then we have IQ, and when we might times that by J omega LQ, that's going to rotate that by 90 degrees, and so we'll have another vector component coming up like this. J IQ XQ. These vectors, they don't have to be the same length. It depends on the current that we're applying. So then the net, when we add those up, would be the voltage Vs. Now remember again, we would have, if we have resistance, we'd have a ID times the resistance and an IQ times the resistance, so it'd have some more vectors in there. So you can see why it just makes it more complicated, but it doesn't really add much to the discussion that the main point of the lecture doesn't really add too much, so I'm not putting it in here. So then the angle between the voltage and the current is the power factor angle theta, and then we can define angle between the q-axis and is, which will give us gamma, and then we can also define a delta, which we're not going to use, between Vs and the q-axis. So one thing here to note is that the ES is, well, I said the ES, we align it along with the q-axis. If you think about it, so you know that so E is equal to the change in flux with respect to time. You know, where you could think of you could imagine the flux due to the magnets was created by some fictitious current source and inductance. Anyway, it's got some flux associated with the magnets. That's what the magnetization flux is. And so if you take the derivative of this, and the flux is aligned with the d-axis, remember from all of the drawings we had, then the d-axis flux you would rotate by 90 degrees because of the difference in the voltage and flux, but with respect to time. And so that's why it makes sense to have the voltage on the q-axis there. Okay, so we can see that the ID and IQ, IQ is equal to the magnitude of IS times cosine gamma, and I'll call that equation 5. Do you have a 4, right? Okay, good. And then ID is equal to IS times sine gamma, which is 6. And then also IS squared must equal IQ squared plus ID squared, and that's 7. Okay. So we can okay, I'll say that later actually. Pardon?
In your last equation.
Oh, that's whoops. D. Yeah, thanks. Sorry. So this that's equation of circle. So now, if the current is if the current is negative, so this is the positive d-axis down here. So if when we say that we have a negative d-axis current, that's up. That's the definition that the US uses. So then we so then if ID current is negative, then Now I won't. I'm not going to decompose it as I'll just decompose the current in this drawing. So we have IQ, and this is ES here. That's along the Q-axis, and then this 90 degrees to the Q-axis must be the D-axis. So this is D-axis, and so we could have a current going in the negative of the D-axis, and then in that case, the net current would be located, say here, and so then putting that together, the voltage could be located like here. So this would be theta, and then this is gamma, and then this is delta. So this is ID. So if you look at this now, the power factor is the difference between the currents. So then so then we by changing the direction of the D-axis current, we could shift the power factor. It does more than that, though. So if ID stator current is negative, it will be so. If you think about the drawing we had, when the flux was in the D-axis positive, that's the direction of the that's the direction of the magnets. So if we apply a D-axis a current, if we have a current that is going in the negative, whoops, that should be D there. That's D. If we have a current going in the negative D-axis, then we are applying a flux from the stator. We're applying a flux from the stator that would be opposing the flux coming from the magnet. So that would reduce the effect of the magnet, right? You're going to be reducing or demagnetizing the magnet. IC stator current is negative. It will try to demagnetize magnet, and then note the power factor will be delta minus gamma. So if you apply the flux to try to go in the opposite direction of the magnet, you have to make sure that the magnet is not going to be demagnetized. In this case here, we had the current going in the direction of the magnet flux along it's going in the positive D-axis, which is the way that we've defined the flux coming out. So then that would increase the that will add to the flux due to the magnet. So we're actually increasing the effective rotor field. So you could actually get to the point where you on the magnetization curve, if you apply it enough, you could actually shift the magnet operating point into the first quadrant. This is the second quadrant. You could go above BR even, because you're adding flux. So ID stator current is, let me put if ID static current is positive, and I'll you will see this in the, I'll write out the equations and it will be more clear than me just verbally explaining it. But hopefully the pictures that I showed help to visualize what the flux in the d-axis means, and then the current creating the d-axis flux, what that means. So if ID static current is positive, it will increase d-axis flux and produced by magnet and move magnet BH curve load line, and it is possible to have BM being greater than BR and move into first quadrant and move into first quadrant of BH curve. Okay. Any questions? Okay, I'll stop there and have a break, and then I'll write up lots of equations. Okay, thanks.